Hi everyone, this is my video for the Spring Math system of the final project. And before we move on to this MATLAB program, we need to have a little bit of the math and the slide I watch. So here's the slide I watch. It's our course slide about mechanical and electrical vibration. And the basic part of this is about Spring Math system. So I actually did a Spring Math system for the MATLAB on the MATLAB. So basically what that MATLAB program did is it recorded the whole x and y, the time and the y position, and it printed on the graph. So it's not an animation. And I get a coefficient from here. So here I actually just take the coefficient into use. So m is equal to 1 out of 8, and gamma is 2, k is 24, and the initial condition for u is 2.5 and 0. So taking these, we can solve the we can solve the damped system. For the undamp and underdamp and critically damp and overdamp, this is a graph that we should have. For green one, this is overdamp, and this one is underdamp, and for this is critically damp. So basically it's about the gamma squared minus 4mk is larger, equal, or smaller than 0. So here I did this, and given y0 is the initial condition, and t-span means the time I want it to print. K is the spring constant. M is what I get from the previous one. It's about the mass. F is force, and C here I actually use it to represent gamma. And C1 here is 2 times square 3, because like 4mk here is 3, so 4mk is 12. So C1 squared, when it equal to 0, it should be 2 times square root of 3. And here's a way, but we didn't use it. And so Ty here, I use a system called Spring Math, and this Spring Math it returns a system function in MATLAB. So if we want to use ODE 45, you need to separate it into 2 first order differential equations. So here is how I solve it. And here times 0, because the slide we have here, it actually solve it as an differential equation with an harmonic equation. I believe that's what it calls. So here is solve it as here equals to 0. So times 0 and move it out of it forward here. So that's why the coefficient look like this. And for the damped spring mass systems, it actually should have minus gamma times v, because of the coefficient about the damping. And after that, the damped spring mass system is the same return system function. Here we have the same things, but sending different gamma value. So after I plot this, it's about the undamped resonance, damped resonant, and critical and damped resonant under. So it should look like this. So like as we looked before, this is what we got. And I actually did a small MATLAB program for the animation, but I didn't have time to modify it. Let's take a look. So this is for the animation, and I modified it from the previous one we had. So when I run this, you'll actually get the damp, like this one we have here. So it draws a trajectory of the ball along the time span, but I haven't modified it for the other two. It actually prints out something weird. So this is what I did for the final project. Thank you.